Thank you. Good morning. First of all, I would like to thank the organizers for this beautiful conference. And second place to say that this work is joined with Marcelina Sevilla and Sebastián Lajara, who are my thesis advisors. Oh well, today I will talk about what are operators with a Kato property, which is a special class. So sorry, but I'm going to start with a definition. So we say that an operator between Banach spaces is called, it's said to have the Kato property if for every finite codimensional subspace W in E, the restriction operator of T to W is not an isomorphism. In other words, where if for every epsilon greater than 0, there exists X in W such that the norm of T of X is less than epsilon times the norm of X. This notion appears in somewhat in the book of, by a result by Cato, which appears in the book of Lindenstrauss-Zafiri. So, the result by Cato asserts that in this hypothesis for any operator satisfying the Cato property, we have that there exists a closed infinite dimensional subspace and satisfying that the restriction of T to that subspace is a compact operator. And later, von van Sevcik in the year 94 improved that result, assuming also that E is a separable Banach space. So in this case, the closed subspace is a one, which is infinite codimensional and infinite dimensional, satisfies also that the image is dense in the image of the whole space E. Later, a result by von Flachara, Trojansky, and Zanko improved that result in other way, but first I want to introduce what is an operator range. We say that a linear subspace R in a Banach space is an operator range if there exists a bounded linear operator T between another Banach space F and E such that R is the image of T. We will look at the class of infinite dimensional and infinite codimensional operator ranges, and in this class we will focus on the set of proper dense operator ranges. Like an easy result shows that this class, the second class, is included in the first. We look at that class because of its relation with the existence of infinite dimensional separable quotients in a Banach space. So we have that by the Saxon and Wilansky result theorem of the year 77, it is equivalent to have a proper dense operator range and to have a closed subspace such that the quotient of E with X is separable and infinite dimensional. Okay, so the referred result by von Flachara, Trojansky, and Zanko says that for a separable Banach space, if we have an operator between E and another Banach space F, we have a closed subspace infinite dimensional, infinite codimensional, and we have an operator range satisfying that the codimension of the sum of R plus L is infinite, and the intersection between R and L is trivial. In the case that T satisfies a Cato-like condition related to L, then we obtain the following. There exists a closed subspace E sub 1, which is infinite dimensional and infinite codimensional in E, satisfying that L is contained in E sub 1 and dimension of the quotient of E sub 1 and L is infinite. The intersection between E sub 1 and R is trivial, and again, the image of T sub 1, T of E sub 1 is dense in the image of E. Well, some class we state that result because it has a lot to do with quasi-complemented subspaces or quasi-complementary subspaces. So first I will introduce them. We say that two closed subspaces in a Banach space are quasi-complementary if their intersection is trivial and their sum is dense in E. We also say that in this case, if X and Y are the quasi-complementary subspaces, Y is a quasi-complement of X, and also we may say that X is quasi-complemented in E, and we say that they are proper quasi-complements or proper quasi-complementary if their sum is not the whole space E. Well, the last theorem has consequences on these subspaces, because if, for example, we have a Banach space E, a pair of quasi-complemented subspaces in E, we have also an operator range. Well, no, it's not necessary. So in this case, we have that taking T equal to the restriction to X of the quotient map between, the restriction to X of the quotient map of Y. So then we may obtain, applying this theorem, that there exists a subspace X sub 1 closed in X such that dimension of X quotient X sub 1 is infinite, and then the closure of T of X sub 1 coincides with the closure of T of X, which coincides with E quotient Y. So X1 and and Y are quasi-complements. Okay. So now I'm going to explain what is the cutoff property, but extended for subspaces, which is the core of this work. What we intend in this work is to extend the previous theorem, but debilitating the separable assumption. So, well, we say that an operator has the cutoff property for a closed subspace L, which is infinite codimensional and infinite dimensional, given that for every finite codimensional subspace W in E which contains L, there exists an X in the containing in W minus L, such that the norm of the image of X by T is less than epsilon times the norm of the quotient of X by L. So we define for L and for the operator T what is the induced operator defined from the quotient of E with L to the quotient of F with the closure of the image of L by T. And this is given by the following formula. So we represent it with a tilde. Then in the work we give the following proposition, which is a characterization. We have that T has the cutoff property for L if and only if T tilde has the cutoff property which we said before, which is the cutoff property for the subspace L equals to 0. And that's also equivalent to the existence of an L annihilator minimal sequence x sub n, satisfying that the norm of T of x sub n is less than n to the minus 1 times the norm of the quotient map of L acting over x sub n. So we are now prepared to assert the main theorem. This is which appears in the work, and we have, as before, an operator from E into another Banach space F. We have L, which is a closed infinite codimensional subspace of E, and we have an operator range. In this case, it has to be a proper dense operator range. And we have only that the intersection of R and L is 0. Well, in the latter theorem, we needed that the codimension of R plus L is infinite and the intersection is 0. So since R is the proper dense operator range, only the fact that the intersection is trivial guarantees that the codimension is infinite. And now we have to assume that T has the cutoff property for L. So if we have that E has a separable quotient, well, in the case for L, if the quotient of E with L has a separable quotient, then we obtain the following properties. We obtain that there exists a closed subspace which is infinite dimensional and infinite codimensional, is a one satisfying the first, that it contains L, and the codimension of L in E sub 1 is infinite. This property B prima, which is a codimension of the sum of E sub 1 plus R, is infinite, and that the closure of that the image of E sub 1 by T is dense in the image of E. And to get the proper condition B, we need to assume that E star is weak star separable. In the case for L different from 0, we need to assume that E, the dual of E quotient L, is weak star separable. So then we achieve the same conditions, the same properties as in the theorem by von Flachara, Trojansky, and Sanko, but debilitating the condition of separability into having a separable quotient and a dual as weak star separable dual. So I will go to with the consequences of the theorem. The first one is diminution of quasi-complements. Here we don't need the assumption of weak star separability. So a result by James and later improved by Johnson said that if we have a couple of proper quasi-complementary subspaces, then in the case that one of them is a weakly compactly generated space, in that was the version of Johnson. The version of James was assuming only separability on X. Then there exists a subspace X sub 1, which is infinite codimensional and infinite dimensional, satisfying that the sum of X sub 1 plus Y is dense in E. So now, applying our theorem, we obtain that we only have to assume that X has a separable quotient. So the reason, the argument is like this, more or less. So the second main consequence is about spatiality in the dual. So if we have an operator T with the dense range, which is 1 to 1, and is not closed, then we may find a closed subspace, which is infinite dimensional and infinite codimensional, such that the quotient between E and X is separable, and its annihilator doesn't intersect the image of the adjoint operator T star. Okay. Well, also, having an operator range R which is proper and dense, we obtain that the codimension of the sum of R and X is infinite. The last main result is a characterization of weak star separability of the dual of a Banach space. So we may recall the classic theorem by Lindenstrauss and Rosenthal, which says that for a Banach space E and a closed subspace X, satisfying that E quotient X has a separable quotient, an infinite dimensional separable quotient, and have an X star being separable, then X is quasi-complemented in E. So here we have, which is an extension of, in some way, an extension of this result in the case that we have also a proper dense operator range in E. So the conditions needed to have that the subspace X is quasi-complemented and this quasi-complement satisfies that the intersection with R is 0, it is necessary and sufficient to have that the E star is weak star separable. So the main one direction comes, direction 1 implies 2 comes by the main theorem, and the direction 2 implies 1 comes by this result by Sebastian and Mark of the last year, which assert that E star is weak star separable if and only if for every operator range, then proper dense operator range, there exists a closed subspace which gives us a separable quotient and doesn't intersect R at all. So I end here the talk. Thank you so much.